Okay, good morning, folks. Welcome to section number 10, the last section. Sad. But y'all are almost done. Y'all have seen all of the content in the class so far. I know that lecture on Tuesday might not have been the most focused lecture viewing experience with a looming exam. Exam grading's underway. We plan on having the grades again by Monday. And the answer key will be released then as well. So far, I think I've graded like 4 questions, and I think like 6 of the 9 questions are graded. So like we are underway. We are trying to get it done. The QR code up for today for attendance things you can scan here. The question is, what's a happy and what's a crappy of the summer? Like highs and lows, kind of. We're reflective, we're at the end of a journey. In terms of content, we are going to try to kind of pick up the pieces and see what the big themes were from lecture on Tuesday. And also another big kind of goal of this section was I wanted to start on a lot of challenge problems with y'all. So I tried to do like 5 challenge problems, or at least chunks of 5 of them with y'all. So we are gonna kind of try to jump into it, see a lot of content. I've also structured this whole section around several kind of big ideas or kind of themes that we're going to come back to. So we will see that organization pop up as we go. But are there any kind of logistical questions before we jump into things? Well then, are we tired of transitions? No. Okay. So let's see what's going on here in our little soundboard. And that is from That's a Raven. But first up, our first big idea are hydrogens on an alpha carbon are acidic. So we learned from lecture 2 that the pKa of an alkane is around 50. But the pKa of these CH bonds that are at the alpha position next to a carbonyl are actually around 20. So they are like orders of magnitude more acidic than we would necessarily expect. And if we deprotonate there, we have this resonance structure up with the carbonyl. So we have a resonance structure that could place the negative charge on the carbon. And you will see some classes where they draw these kind of enolate structures like this. That's not our preferred method for this course because between these 2 resonance structures, which is more stable? The negative charge on the oxygen, right? Because oxygen is more electronegative. So this is a stabilized negative charge because of resonance. So we would say that this is a relatively weak base, making this a relatively stronger acid than something just like an alkane. We do have an MO requirement of this, kind of like our MO requirement of anti-periplanar for E2. And our MO requirement here is that we want our sigma CH of the hydrogen that's going to get deprotonated to line up with the pi star CO over here. So we want to make it really easy so that when a base deprotonates it, the electrons from the sigma bond can just kind of slide over into the pi star and break the pi bond. This is not something that you're going to have to deal with a lot. Like, this is really only one challenge problem that we're going to do together for the most part. So this is not something that you have to think about nearly as much as like E2 on a chair. But this type of MO requirement you'll see a lot in Chem 27. And actually this enolate chemistry happens a lot in nature. And so you'll be seeing these types of reactions more and more again. So big idea 1, the alpha hydrogens are acidic. Big idea number 2 is enolates are nucleophilic at the alpha carbon. So if we push down to reform a carbonyl, then this double bond can go and attack an electrophile, and we will create an alpha beta bond. We will create a new bond to the alpha carbon. This is a thing that like feels kind of like I don't know, it's like combining a lone pair push with a nucleophile attacking electrophile at the same time, which just feels kind of like a stronger lone pair push. And you can think about this is like a pretty strong nucleophilic attack, and so we don't need the most amazing electrophile like we saw with EAS reactions. We have some like small distinctions just to touch on. So If we have a negative charge on it, it's an enolate. If it's neutral, it's an enol. Enol comes from an alkene plus an alcohol, enol. And the ATE ending is like the difference between an alcohol and an alkoxide. Like, it's just what we do to say it's negatively charged. Cool. So, which do you think is the stronger nucleophile? The one with the minus or the one that's neutral? Minus. It has a buildup of electrons, so it's going to be a better donor because it wants to kind of spread those out more. Which of these do you think is more stable in base? Maybe a different question, which is more stable in acid? In any of your acid mechanisms, do we like having negative charges? No, because the negative charge would be protonated so easily. So which do you think is happening in acid? The enol, the neutral one. And the one that happens more in base is the enolate. So this is the thing of, if you are in basic conditions, you'll form these enolates, which are better nucleophiles that can go and attack something. Whereas when you're in acid conditions, what you might have to do is you might have to protonate a carbonyl to make your electrophile better, because your enol nucleophile isn't as strong. Cool. So this is just kind of terminology, enol versus enolate. We also have this kind of phenomenon called keto-enol tautomerization. So has anyone ever heard the word tautomers before, or tautomerization? So tautomers are things that are kind of logically equivalent to each other. And if we look at these structures here of this ketone and this enol, they both have the same molecular formula, this R with a C2H3O. And so we say that these, being kind of constitutional isomers of each other, they're tautomers of each other. Like, almost everything is in the same spot, except for we've moved an H from one of the H's over here, and we've moved where our double bond is. So the powerful thing about this keto-enol tautomerization is a ketone normally an electrophile or a nucleophile? It's an electrophile. It has that good pi star CO. But we just said enols are nucleophiles. So it's a really kind of powerful way, and this is a nucleophile at the alpha carbon, so at this position here. It's a really powerful way to make a molecule either into a carbonyl, or a carbonyl, which is an electrophile, or an enol, which is a nucleophile. And so it can do these both kind of functionalities. Now, we can form enols both in acid or in base, and I've just presented the mechanisms here. The big distinction here just has to kind of do with protonation states. Like in base, we can deprotonate right off the bat, and when we do, we form the enolate, which is okay because we're in base, and then we can neutralize it. But when we do it in acid, we can't just straight up deprotonate this ketone with water. It's not acidic enough for that to happen. So we have to protonate the ketone first to make it even more acidic, and then we can make our enol. So we are accomplishing very similar goals, and we are having very similar steps of like alpha deprotonations in both of them. The protonation states are really the main thing that are changing. So questions on these kind of first two big ideas. Hydrogens on the alpha carbons are acidic, and enolates are nucleophiles of the alpha carbon. Okay. So we have lots of different flavors of enolates, and so this feels very much with the same energy of like, oh, is it here? Oh, my soundboard. I'd geared it all up. I'd set it up with a little pitch. It feels very much like the energy of, choose your fighter. Who's your nucleophile? And they're all kind of the same over here. So we have our classic ones of the aldehyde and ketone going and forming an enolate. We could also have an ester enolate that's a little bit less acidic. And we can even do things as weird as having a nitrile enolate. And like, this looks really strange, but it would function just like an enolate. You can kind of push down, and then there's double bond attacks. And then the only thing that's more acidic than like an alpha hydrogen to a carbonyl is a hydrogen that's alpha to two carbonyls. So when you are in these dicarbonyl systems, you are even more acidic, even lower pK values. The last one I want to point out is kind of a weird cousin here. This enamine is really similar to like an enol, because I mean, again, the name en and amine. But this can also do a push down and attack, and we might see that coming up soon. So let's jump into some of these like problem set problems that talk about enolates and these kind of basic questions and see what comes up. And oh my gosh, what functional group do we see right here? The enamine, which we said can be a nucleophile like an enol. Okay, so if we know that that molecule is a nucleophile, then what are kind of potential electrophilic sites on this other molecule? Maybe instead of sites, could you tell me acceptor orbitals? Yeah, so we could attack the carbonyl pi star CO. Any other acceptors? Sigma star CBr. Do we agree? Now, which of these is the better acceptor, just in terms of energy level? The pi star, because we know that's lower in energy. But does it look like we actually reacted at the pi star? No. It seems more clear that, like, this carbon here, this carbon made a bond to another carbon. Well, where do we have another 2-carbon chunk in our nucleophile? We have the, like, nitrogen bits, but we know that the nucleophilic position is going to be like if we kind of push down and this goes and attacks, it's going to be this far carbon at the end, this kind of alpha carbon. So we know that we are going to be making that connection, and that's how we could tell that even though with our MO energy levels the pi star might be a better acceptor, this is the reaction that actually takes place here when we're given our products. So let's draw some arrows and try to get there. So we are going to push down from our enamine and then have the alkene go and do a backside attack and kick off a bromine. When we do that, our product here is, we've left the O untouched. We've made this kind of blue-red bond. And this is a hydrogen. We now have a double bond to nitrogen there, and that's part of a 5-membered ring. And so our nitrogen is going to have a positive charge now. Okay. So now we have this kind of iminium thing, and we have the reagent H3O+. Does that ring any bells of reactions that might have been exam 2 reaction responsible for? Amine hydrolysis. So I'm going to let y'all write up the rest of the mechanism on your own, but this is just straight up the amine hydrolysis mechanism. In lecture 5. I'm going to make the arrows look a little bit nicer. So, not too hard. It's kind of introducing these new like enolate-like things and new enolate attacks with some of our existing mechanisms. So that's challenge problem 4b. If we look now at challenge problem 1, basically it's asking for us to justify why does one of these ketone structures have a pK of 40 and the other molecule have a pK of 20. So which of these numbers around 20 or 40 is normal for like an alpha hydrogen? The 20. This is what we would normally say of like the alpha hydrogen normal. But a pK of like 40 is like close to just an alkane. So we need to figure out why this right one is way less acidic. So can you take a minute and try to write out just what are all the alpha carbons to your carbonyl? Like just identify them real quick. We have the carbons on either side of these carbonyls. So why don't we try to draw the enolates that would be formed if we deprotonated at each one of these sites? if we did this left one, we would have that O minus. Oh, also these things are hard to draw, and we don't really teach you how to draw them, right? And so it feels like a little weird. So I'm going to show you my way of drawing them. So I start off with the kind of slightly slanted line. Then I do 2 parallel lines up. Then I do 2 parallel lines down, and a line between them. And then I create my bridge. We're not going to be asking you to do these on exams, and even if we did, we would not like grade your drawing, you know. So the other anole that we could form over here is on this side. And then the last one would be like, ooh, gross. A double bond here on this kind of bridge thing. And here, we could do on either side since it's symmetric and it wouldn't matter. Okay. So, do any of these structures raise some alarm bells for you? Maybe thinking back to lecture 4. Lecture 4 talks about double bonds. Why does this bring alarm bells? Said with much enthusiasm. Yes. It violates that double bond rule from lecture 4. That double bond rule is called Brett's rule. So, violates Brett's rule. Like, how do I draw it? Oh, like, I mean, you could draw something that would look like a base. He pronates here, pushes up, pushes up. But this structure, this double bond, would never happen because Brett's rule says you are never going to put a double bond on a bridgehead atom. So bridgehead atoms are atoms in the ring where there is a bridge. So here, these atoms are never going to have a double bond to them. And it has to do with the fact that if we have a double bond, we want that 120-degree angle, and the strain of being at a bridgehead position just doesn't allow that. So this violates Brett's rule. And then one over here also violates Brett's rule. But that's still a double bond to a bridgehead atom. So, canceling both of those. We only really have one option that forms. And so this is our enolate. So in the other cases, there just wouldn't be that resonance stabilization. This question also asks for like an MO justification of this. And the way that we can do that is we can draw the pi star CO. And we can talk about how this sigma CH can line up with that pi star CO. And that was the MO requirement that we talked about earlier. There are special requirements on a ring, but outside of this question, we do not ask you about it for this course. So that would be the kind of overlap here of the sigma CH into the pi star CO. And then if we tried to do it over here, like this would kind of be our double bond, pi star. And then our hydrogen would be kind of going down away from it and maybe like perpendicular. And so like this is just like no/poor overlap of the sigma CH and the pi star CO. And that's kind of on the acidity of these two with this weird bridgehead structure. So it's more kind of theory based. In this bottom part, what's the main difference between these two molecules, the starry material and the product? There's a deuterium here. Any other carbons move or anything special? No. So over here in the original, we have a hydrogen that we somehow need to remove. And what type of hydrogen is this? It's axial, but in relationship to the carbonyl, what is it? It's an alpha hydrogen, and we know alpha hydrogens are what? Acidic. So we can have our OD minus, which is like OH minus, come and deprotonate the hydrogen. That folds in, makes a double bond. And this is also a Kirsch chair. We would kick off HOD. And then we need to grab a deuterium. What would we grab a deuterium from? D2O. So that's heavy water, essentially. So we push up, grab a deuterium, and then we're done. So we did like an alpha deprotonation, followed by an alpha, like an alpha deuteration, I guess, or deuteration, something along those lines. Yeah. So it's just kind of undoing it and redoing it. And the question's kind of going to really ask, hey, why did you do that rather than this hydrogen? And it has to do with that orbital overlap of like this sigma bond is going to line up better with the pi star when it's axial rather than the other one on the other side, which is equatorial. I mean, I would draw the picture and then like say something about it, but yeah. Not taking a picture of the answer. Wow. Wow. So these are kind of the basics to get us started. Are we ready for our first kind of big family of reactions? I see no. I see indifference to mild amusement to fear. Those are the emotions I'm seeing. But let's do it anyway. So the aldol reaction. Our big idea here is that enolates as nucleophiles can attack ketones and aldehydes. So when we do this, maybe we'll kind of start with the mechanism here. We first need to form an enolate, and then that enolate would just go and push down. Alpha carbon attacks a carbonyl, a ketone or an aldehyde. When that happens, we get to this structure where we have an O minus here. And the big thing that we've done is we've created a alpha beta bond. Alpha beta bonds are going to be the name of the game for the next like couple sections. So always be counting your alpha beta away from a carbonyl here. So this O minus, there's not really much that we can do with it. We don't have a leaving group or anything. And so it's just going to get protonated. And we get to our first kind of stable product, which we call the aldol addition product. This, the kind of government technical name of it is a beta hydroxy carbonyl, because we have an OH group, a hydroxy group, beta to our carbonyl. So do you remember like in the imine mechanism where we had that neutral hemiaminal that was kind of stable for a moment? This is even more stable. Like the reaction could fully stop here and this be the product, this be the answer. Or it could go on and react more. And we have ways of kind of controlling whether we stop here or whether we react more and go on to this condensation product. And typically it's like we just do the reaction with more heat and it will react further. But this is the first thing to be on the lookout for, this beta hydroxycarbonyl. And the kind of nickname of a beta hydroxycarbonyl, because it's a lot to say beta hydroxycarbonyl over and over, is we call this an aldol. Because it's like an aldehyde alcohol. But you gotta remember that's beta. If you do it like alpha, that's not an aldol. We don't call that an aldol. So, once we are our aldol addition, we still have alpha hydrogens present, right? So we could deprotonate this again, make another enolate, and then we do this weird step where, you know, like when you're kind of playing in a pool and you're wanting to make a big wave or something, this would be kind of like gathering water towards you and then pushing it all in one way and then like knocking your friend off to another part of the pool. So that's what happens here basically with atoms. We are trying to do this lone pair push, reform a carbonyl. When we do that, we move our alkene over and we kick off an OH. Now we know OH, that's not a great leaving group, right? And so if this was just a typical like lone pair push situation, we might not do it as readily. But because we're doing this kind of build up and we have this stronger action than just a simple lone pair push, we are able to push the OH off. It also is happening in base, and you're better able to kick off an OH minus in base than acid because it's more stable in base. So this step has a special name. It's called an E1CB mechanism. It's E because we form an alkene and we've kicked something off, so we did an elimination. And the CB here has to do with the fact that this is the conjugate base of some acid. We won't ask you to supply this name, E1CB, but again, I think it's helpful to have those arrows just to kind of see. Because I think another thing a lot of people like to do, like a common mistake, is they do this deprotonate, here kick off. And that would be like -2 points. And I want you to get the points. The reason why like this arrows doesn't happen of just like kicking off directly here is because those electrons are going to go into resonance here with the O. So what we get out of it, we call a condensation product. And we call it a condensation because like OH, like water, has left. And so this functional group you've seen before. What is it? All these throwbacks. Lecture 3 coming back at us. So the government name is an alpha beta unsaturated carbonyl. So we would have a double bond, which we can sometimes call unsaturations. You might remember from bio classes like saturated versus unsaturated fats. It has to do with it having double bonds. So this is just saying our unsaturation, our double bond, is between the alpha beta. Cool. So that's the basic idea of it. Let's kind of mess around with it and like do some arrow pushing together. So this is challenge problem 7. Challenge problem 7 has this thing that looks really scary, but she's kind of irrelevant and is just there to look scary. So I've just called it R. So here, there is some kind of weird stuff going on where like it doesn't look like we have a aldol or a enone in our product, right? Like, do we see a beta hydroxy? No. Do we see a double bond, a carbon-carbon double bond? No. We've just kind of added these like carbon things. So we'll get to that in a bit, but maybe let's start off here with we're in ethoxide, we're in a base. Do we have any acidic alpha hydrogens? Yeah. Is it in molecule 1 or molecule 2 here? 1. So 1 has these 2 alpha hydrogens that are between 2 carbonyls, and we know that they're super acidic if they're between 2 carbonyls. And on the other one, do we have any alpha hydrogens? Well, this, it's not on an alpha carbon, it's on the carbonyl. And so we would not call that an alpha hydrogen. And then the R group here is like the start of a benzene. And so that is going to have 4 bonds to it, no hydrogens. So if we're thinking about which of these to make into an enolate, which is the nucleophile, and which to have as the electrophile, we only have one option for what's going to be the nucleophile, right? It's going to be this left molecule here. So we're going to have our OET minus go and make an enolate. And this is our nucleophile now. And then we have our electrophile over here. So, I want you to try to recapitulate the arrows of this aldol reaction that's right above, where we are now at this step where we have our enolate and we have our ketone or aldehyde. And I want you to try to get to the aldol addition product, which I'll draw the structure of. I want you to try to get to the aldol addition product, and then also get to the aldol condensation product. So that's the condensation product. And the addition product is like this. So these are some kind of guiding structures, but I want you to try to draw the arrows and piece it together for a minute. Actually, I'm going to scroll up so you'll be able to see the steps. So, can I get a volunteer to talk me through the first few steps, starting with your nucleophile and electrophile? Alyssa. Mm-hmm. Mm-hmm. Excellent. So we've pushed up, and we are having this alpha carbon over here attack the carbonyl carbon of this electrophile. Beautiful. But we don't go directly there, right? Like we have an intermediate first, where we have now our two carbonyls. And we have an O minus here. So what else do we need to do to get to the aldol addition product? Or protonate. Yeah, yes, exactly. So we're just going to grab it from HOET, or you could use your SOL abbreviation. So that totally works. Okay. Can I get another volunteer to help with getting us from the aldol addition to the aldol condensation product? Oh my gosh, volunteers that are springing out. It's overwhelming. What do I do? It's okay to be wrong, and actually, it would be more helpful if you make mistakes because then other people can learn from it too. Sure. Yeah, the alpha position, great. And then you. Okay. So does it matter that top one versus the bottom one? What do people think? It doesn't matter. It's symmetric, so totally right. So we have now yet again an enolate, our new favorite functional group. And then what'd you do? We pushed our friend out of the pool. Yeah, we did our E1CB mechanism, and we get this. Um, I actually remember the reason I make such a big deal out of this is because I remember being so bitter. Taking this chemistry is normally taught towards the end of OChem 2. I remember taking this exam and studying my butt off, and then getting counted off like 4 points because I just deprotonated it. Like, I did this and kicked it off. It was like -4, missing E1CV step. And I was like, the nerve, the audacity, the gall, and the gumption. But here we are. Here we are. So, we first had our like aldol over here, and then now we are at our enone. And then this second step reagent, what does it look similar to? It looks similar to NABH4, and we have a CN here, but based on how it's written, you couldn't totally see how it's working. The CN is bonded to the boron. It's not kind of, like I can see the Strecker similarities too. So this is a variant of NABH4 that only adds 1,4 to an enone. Yeah, so we were kind of completing the picture from lecture 3, where lecture 3 we said if we have sodium borhydride, we sprinkle in CCl3, it'll only do 1,2. And then this is the version now that you were learning that will only do 1,4. You will not be required to like know this for like exams. This is just kind of like, hey, it exists, and in this case we're going to use it. I think the question has like an explanation of it in the instructions. So what we're going to do, so we have our BH3CN, there's a minus in the boron, and we just do a hydride attack 1,4 and do our normal like conjugate addition arrows. Again, it could go to the top carbonyl or the bottom one. And we've added a little hydrogen on there. And so now we are so close to our product, what's the only difference that we need to do? What's the difference between this and this? We make the carbonyl. If we push that carbonyl down, we can do something with a double bond. And so what's the double bond going to do? Yeah, so we have a hydrogen here that we don't have in our intermediate. So we are going to do a alpha protonation, and we're going to take it from our solvent HOET here. Now you could also just do H-sol. That's fine. Excellent. So, again, we're kind of trying to combine new stuff with old stuff, and this is where the class, I think, has a lot of like full circle moments with some of your first reactions that you learned. Speaking of first reactions that we learned, looking at challenge problem 2A over here, what reagent is this? Grignard! Does it look like we did a Grignard attack of the carbonyl? No, we would expect something that would look like OH and our phenyl, right? Like that's the thing that we would expect from our lecture 3. Where did this phenyl end up? Benzene, okay. And then if we have this starting material, we see that twice over here. So 2 equivalents of this reacted with itself, and it made what functional group in this product? Enone. So we know that we can do that from the aldol condensation. And then somehow our Grignard turned into a benzene. So if this is not acting as a nucleophile, how is it acting in the reaction? It's acting as a base. So we need something to go and grab a alpha hydrogen, and we know our Grignards are very basic. And so it can just go and grab the hydrogen, push up, make an enolate. And what we are left with is now we've added a hydrogen onto our phenyl group. And so that's just benzene. So now, this is the nucleophile, and it's going to attack another equivalent of itself in the carbonyl form as the electrophile. push down, do this attack. And when we do that, we've made this alpha beta bond. And at this point, what would be our normal step in like the aldol addition? Like, what would be the next thing that we would do to get our aldol intermediate? We would protonate it. Yeah. So, here, if we are just in step 1, do we have a source of hydrogens that we could just protonate this with? No, we don't. Because here, diethyl ether, it's not like methanol. We don't have a protic solvent here. And then here, this is not going to be a strong enough base to deprotonate a benzene. So we are going to have to fully go into step 2 and grab this from an H+. So this is now step 2. And we're going to go on, and I'm going to let you fill out the rest of the steps here, but the key thing that's tricky on this is we are now in acid. So that's going to change your protonation steps of the aldol reaction. I've given you the version here in base, and then you also saw in lecture the version of it in acid. And so because we are in our acid workup step, we are going to be doing all of these steps in acid. Same idea will be there, but just different protonation steps. You're not going to have negative charges. So that will be for you to finish up on the problem set. Now we're still on the same topic, but there's like a mini transition. Can I play another transition for you? Let's see. Where's one of the Hannah Montanas? So our next big idea that's still within aldol is we can get a lot of different specific reactions from this general idea of an enolate attacking a ketone or an aldehyde. And these all kind of are in the same family of reactions. We could have a ketone or aldehyde attacking itself, the exact same molecule. And then this is what was the classic aldol reaction. This was the first one that was discovered. But if something forms an enolate and it attacks a different molecule, a different ketone or aldehyde, that would be a crossed aldol. We could also have the enolate and the carbonyl electrophile in the same molecule and do an intramolecular attack. Or every step of this is reversible. So we could do starting with an enone and going backwards. We can go in reverse. And then we would get 2 ketones. So my way of thinking about this, which I'm really surprised I have not seen in more of like the organic chemistry textbooks, is I think about these in terms of their cha-cha slide concordance. So do we know the cha-cha slide? Is that like a generational thing where like my millennialism is showing? Okay, we know the cha-cha slide. So the first one, where it's these 2 molecules that are exactly the same right next to each other, that corresponds to, of course,
slide to the left, slide to the right.
Where they are the same thing. They are just right next to each other, doing their little dance. And then what do you think the crossed aldol is?
Crisscross, crisscross.
Great. And then the intramolecular aldol, it's kind of like a molecule is wiggling and doing a little dance with itself, and so it is.
Cha-cha, real smooth. Let's go to work.
It also has the energy because it's all within the same molecule of.
Last time it gets funky.
Yeah, it's doing this weird little dance on itself. So, and then, of course, the retroaldol is going to be.
Reverse, reverse.
And then also the take it back now, y'all. And because we're here doing the cha-cha side, we also have to do the obligatory.
Freeze! Everybody clap your hands. Come on, y'all. Check it out, y'all.
Again, I'm very surprised it hasn't appeared in more, really any of the major organic chemistry textbooks, and so they really need to get on it. But I remember thinking like 2 years ago, how do I kind of like organize these? And I was like, obviously the cha-cha slide. So We would never ask you the exact name of them, but I think it's helpful for y'all when you are looking at reactions and seeing all the kind of crazy things that these can do to have a way to mentally compartmentalize and organize them and see these different types of reactions that are taking place. Yeah. They are all the same mechanism. They are all the Aldol reaction. Mm-hmm. They're just like slightly different variants of it. And the variants really are only in the R groups, so it's nothing with the arrows. I have put the retroaldol mechanism here. It is beat for beat, arrow for arrow, the reverse of the aldol mechanism. And so I will let you do that practice on your own. One thing I do think would be helpful for us to do together is to do some practice with disconnections. So, how do we spot an aldol reaction having happened? We either look for an aldol or an enone. And really specifically, you need to make sure that you know that the aldol is the beta hydroxy, a hydroxy at the beta position. So what I want you to do is in these three molecules, identify the alpha and beta positions and draw a line to disconnect between them because we know the aldol creates an alpha-beta bond. So take a minute, label these, and draw your kind of cut line. The first two aren't too terribly bad. Well, what about this third one? Where's our kind of enone or aldol? Over here? So, it's always going to be in relationship to a carbonyl. So maybe let's go out from carbonyls first. So is this an aldol? Why is it not an aldol? This is an alpha hydroxy. So that's not our aldol product, that's not our reaction. And then, do we have an enone, like up here? No, why? We have this sp3 carbon in the middle of it. So, not an enone. So, where do we disconnect? We don't, because this is a trick question. Oh my gosh. Oh my godness. We have to stay vigilant. Never again will we be tricked. But the other ones, we can do. So with doing our disconnection for the aldol, we have this kind of left side and the right side. Which side do you think was the nucleophile enolate? Can I hear like a left or a right? No one said it with their chest. Think about the mechanism. In our mechanism here, if we had our enolate over here go and attack, and like here attack the carbonyl, she stays a carbonyl the whole time. So our nucleophile one is the carbonyl. And then our electrophile is what either is the OH or it's what was kicked off. So based on that, let's try one more time. Our left or right, which was the enolate nucleophile? The left, because it has our carbonyl. Great. So the way we would disconnect it is we would make the left one an enolate here, and we would make our right one a carbonyl. And if we wanted to go back even further for our enolate, that enolate would be made from this molecule, and we see this was a classic aldol that made it, two equivalents of the same molecule. Similarly, over here, left or right, which of these was our enolate nucleophile? So which one has the carbonyl, the left or right? The right, and the carbonyl is where our nucleophile is. There we go. So we're going to do that enolate on the right, and then carbonyl over here, and that's technically an aldehyde. And we can go back and do it one more, and we would get our aldehyde stays constant, and then we have a ketone. So this disconnection practice I think is going to be helpful for challenge problem 3 here. So, what functional group do we have on our starting material in this problem? Using our new lecture 10 functional groups related to the aldol reaction. In the product we have an enone, yeah. And so that's like an aldol condensation product. And then do we have any aldol related functional groups in the starting material? What are the ones that we're looking for? We're either looking for an enone or an aldol, right? In aldol, what position does it have to be at, alpha or beta? If we go here and do alpha, beta, do we have a beta hydroxy? We do indeed. So we have an aldol. So this type of problem is one that I think about this dance. I don't know what the dance is, but the dance is like where someone kind of goes down and then like pops up, and then goes down and pops up. And I asked like the 8 a.m. section. I asked the 8 a.m. section, and what they said was the Rasputin dance. Okay. So this I think about of the Rasputin dance of we have a product that's this ring that's kind of the down part, and we need to go backwards and go to the straight chain. We need to make it big again. So let's do our disconnection here and see what it would look like as a straight chain. I also want you to try to do a disconnection over here with the enone. The same exact thing that we did over here. Try it out on your own, and then we'll check it, okay? Yeah. I can look it up. I don't have it. Rasputin. Do your disconnections while I'm doing it. Oh, this is Just Dance.
Yeah, it's Just Dance.
While you're doing your disconnection. There she is. So let's check our disconnections. So we know that the carbonyl side of each of these is going to be our enolate nucleophile, and then the beta position is going to be where our electrophile was, so we should have a carbonyl there. How'd you do? So, what's the difference between these two molecules? It's our double bond here, right? Like one has the double bond on the outside, one has it on the inside. And so, if we wanted to go and see what our carbonyl version of this is, we could go and grab a hydrogen from water. And what we would get is this 1, 2, 3, 4, 5, 6, 7 carbon chain. Like this. And then we could deprotonate from the other side of it. and get to the other enolate. So the steps that get us here to our disconnection that we wrote, that would be our retro aldol mechanism. And then this would just be our normal aldol condensation. So the big thing is just being able to pop open our aldol, get it to our straight chain, and then just pick a different enolate to close back up into a ring. And we see that here, if this carbon 3 enolate attacked, we would make a 1, 2, 3, 4 carbon ring, and that's what we see. Whereas when this enolate attacks, we would make a 1, 2, 3, 4, 5, 6 carbon ring over here. So we have options. So that's the kind of basic idea of these questions, which I really love. I think that these are great questions. Cool. That's aldol. Easy as that. Any questions before another transition? So the Claisen reaction is really similar to the aldol reaction, where we have an enolate nucleophile, but now the thing that we are attacking instead of a ketone aldehyde is we're attacking an ester. The fundamental difference when we are attacking an ester is once we've attacked it when we're at this tetrahedral intermediate, if we attacked an ester, we have a leaving group. We have an OR group that can be pushed off. Versus when we attacked the aldehyde or a ketone, we would have like a hydrogen or like a carbon chain here that we couldn't kick off. So when we have a leaving group, this O that was just attacked can reform its carbonyl, do a lone pair push, kick off, and we form this beta dicarbonyl. And ultimately, that's going to be our product over here, a beta dicarbonyl, two carbonyls related to beta to each other. This could be one of them a ketone, one of them an ester, which we would call it like a beta ketoester, or we could have two ketones, beta diketone. The flavor doesn't matter as much. But when we form this, like at this step, we're not done yet, folks, because we are doing this in base. And we have just made a dicarbonyl, and is this hydrogen more acidic than the one that we started with? Yeah, because it's alpha to 2 carbonyls. So if we have basic enough conditions to deprotonate here, we sure will have basic enough conditions to deprotonate here. So since we're still in base when this is formed, we have to deprotonate here and push up. And then we start our acid workup, like our part 2 H plus here. And when we do that, we literally undo it. We literally do an alpha deprotonation followed by an alpha protonation. So this is annoying. But also, if you stopped here and you did not do those last steps, that would be minus 3 points. Because this does happen. And this becoming the enolate version before the acid workup affects what else can be in that reaction beaker. So, I don't want you to lose points. Do the annoying steps. You can do the arrows, I know you can. Let's try a Claisen mechanism together. So, we have some esters here, we have a strong base, and when we're doing a Claisen, typically we make our base the conjugate base of whatever the OR group is on the ester. Just because we could have this interacting with the ester and we don't want to necessarily change the identity of this OR group. Okay, do we have alpha hydrogens? Yeah, we have some on both sides, right? So we could do here or here, doesn't matter which we do. No, because what about the molecule? Symmetry. So I'm just going to arbitrarily start over here. We make our enolate. Our enolate is here. We have an ester on the same molecule, so we're doing our intramolecular Claisen. This would attack. And when we do these kind of intramoleculars, this is when we bust out our little superpower tool. We number our carbons. So we know that's going to be connecting this alpha carbon of the enolate, the carbonyl carbon over here. So we have a 5-membered ring. And when I do this, I'm going to make this 5, this 1, 2, 3, 4. I'll do that in red. So 5 is going to have an O minus, an OME on it. And then 1 is going to have a dangly bit of this ester. So we have an O minus here at the beta position. We have a leaving group. We can just kick it off. And we get our beta dicarbonyl. So that's this. Done. Any questions? Everything good with this? We have to do the annoying step. This would be -3 on an exam. It happens so quickly. It happens so quickly. Don't let it happen to you. Stay vigilant. So, what we have to do is we made a dicarbonyl that has an acidic alpha hydrogen. So we have to deprotonate it here. Thank you, Niyar, for catching that. Push up. And then we completely undo it. And then we get there. It's sad, but it's true. We have to do it. So that's kind of seeing the Claisen mechanism in action. It's a little bit shorter than the aldol one. I think it's a little bit easier. Here we have another challenge problem 3b, which is our Rasputin dance, where initially we have a methyl group over here, and then seemingly it's kind of jumped over here. What has really happened is we've done our bon blah, and then we have to go back to a different ring. So you are going to be doing a retroclaisen, getting some sort of straight chain, and then doing a different claisen with a different enoid. So that's just kind of the reaction scheme for this. I'm going to let you work out the basics of this. But the claisen I generally kind of am wanting to do a lighter touch on because we've just done aldol. So you've seen the big ideas. Again, there's the claisen diaspora of you have the classic, the cross, the intermolecular, and the retro versions of it. The retroclaisen mechanism is the exact same thing in the reverse. We don't necessarily have the annoying step because we no longer have a dicarbonyl anymore in our product. And then claisen disconnection is going to be a pretty essential skill as well with the aldol disconnection. I'm looking at time. I'm like, do we have enough time to do this? Yeah, we do. It's important. So I want you to find the beta dicarbonyls. And when you have 2 beta dicarbonyls, you'll have 2 ways of drawing your alpha beta. So I want you to try drawing the alpha beta from one carbonyl and then try drawing the alpha beta from the other carbonyl. And then we will go through and talk about how they split. So, the dicarbonyls in the first 2 are pretty easy to spot. And like if I start counting from this carbonyl, this would be alpha, this would be beta. But if I start counting from the other carbonyl, in the green here, this would be alpha, this would be beta. So we have two different ways that we could chop and disconnect here. Same thing over here. And then where'd you get the alpha and beta here for the beta dicarbonyl? Trick question, trick question. Y'all are primed for it. So we don't have any beta dicarbonyls here. This is like an alpha dicarbonyl. Here this is an alpha beta gamma. Ooh, but we could have had like an aldol here. Ooh, sneaky. But let's try these disconnections. So if I disconnect over here with its blue line, alpha beta, then I'm going from this carbonyl and I'm saying that that carbonyl in blue over here was the enolate. So that enolate here. And then if this is the beta position that was added, with the Claisen reaction, what functional group are we attacking? Esters, oh my gosh, yes. So, here we have just some ester. We put an OR on it. You can do methyl or ethyl, whatever. So that's one option if we cut that way. If we do the other cut in green here, then our enolate is on the right side, and the left side was our ester electrophile. In this case, we see that both these are equivalent. Like both of these are going to be the same nucleophile electrophile combination. So that's nice. So now, over here, it's a little bit more complicated when one of them is the ketone and one of them is an ester. And basically, when you have it this way, you know that your ester is never going to be a beta position. Because if you attacked an ester, you would be kicking off a leaving group. That's kind of the fundamental idea here, where this carbon that's attacked is the beta position, alpha beta, and it would be losing an ester. So the only way that this bottom one could have been an ester is if you had had something like this starting material. And we don't do anything that looks like that. So we are just not going to do that. So this blue option is just like fake. That does not happen. The other way to remember it is we always call it a beta keto ester. So the main one that's important, the one that we think of as like the kind of parent and not the substituent, is the ester here. So we're going to chop between this alpha beta position, and then our bottom one is going to be the nucleophile. And our top one was the electrophile. So we need to do some OR to be our ester. This electrophile, nucleophile. You're going to get more practice with this as you do more problems, but just know that the disconnection and connection skills for this lecture are really, really critical. Yeah. Because if this was the beta one that was attacked, you would need to essentially have this structure where you have an OMe here. You're like a diester on the same carbon. And this doesn't react the same way as like a normal ester. This is an oxidation level of 4. And like y'all don't really learn any reactions with this. Yeah. Cool. Any questions on the Claisen reaction? I know we went quicker on that. The energy is high post-exam too. It's just palpable. Y'all are pulsating, you know? So, you've already started to see some things that maybe you're a little sus about. A lot of the ones we've done, we've given you the products. What if we ask you to predict the products? So I've gotten 2 ketones here, and say we add NaOH and we do an aldol. I want you to try to think through, just for like a minute, which of these products do you think would form? take a minute, think about the enolate, think about the electrophile and the ways that we could add them up. So, on your hands, we have 8 options here. Can you tell me how many of these you think are going to be made? On 1, 2, 3, 4, 5, 6, 7, 8. How many did you find so far? Okay. 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 So, correct answer is all of them. So, like, if you make the enolate over here and attack another equivalent of the same one, that's how you get A. If you attack the other one, you get B. If you made the enolate inside on the red-orange one and attack this one, C. The green-blue one, D. Then you can do the same thing with the green-blue one. So, like, chaos. Chaos. We need a way of controlling the chaos. And so our next kind of big idea here is we can limit the multitude of potential products by using symmetry, molecules that lack alpha hydrogens, ring size, and sequential addition. So I'm going to go through these pretty quickly, mostly just because the ideas themselves I don't think are that challenging. And I want to make sure that we get to the ending bits. So here, all of these molecules are symmetric. So whether or not we form the enolate on the left or the right, they are going to be the same enolate. So that's a way that we can control the chaos, and we cut the options in half now if we just have a symmetric enolate. We also have the concept of one-sidedness. Like, we could just make it so that only one side has alpha hydrogens. So like here we have alpha hydrogens, here we have alpha hydrogens, here we have alpha hydrogens, here, and here. But on the other side, we either have like a benzene ring, no hydrogens, we have an oxygen, we have a tert butyl, or like we are part of an aldehyde, so none of them are alpha hydrogens. And we can even take that one further. Let's say we want a molecule to only be an electrophile and not make an enolate at all. We can use molecules where there are no alpha hydrogens. Here, on both sides, we don't have alpha hydrogens to our carbonyl. So that means this will be only an electrophile. And then this one's kind of cool of ring size. And this we've been kind of exploring with our Rasputin dance thing of, well, we could either form an external enolate. So the external one here would be like this. Maybe I'll do it in red. And if we do that, we would make a 1, 2, 3, 4, 5, 6, 7, 8-membered ring. So that would form this. Or if we make the internal one, that would be a 1, 2, 3, 4, 5, 6-membered ring. Which is more stable, a 6-membered ring or an 8-membered ring? A 6. That's because it has all the nice staggered interactions or stable chair structure. So even with we talk more about small rings being strained, larger rings also have some energetic costs to them. So over here with the internal versus external, if we do on the external, we would get a 1, 2, 3, 4, 5, 6-membered ring, which is favored. Or if we did on the inside, that would make a really small and strained 4-membered ring, where we would connect 1, 2, 3, 4. Okay, and then the last one, we have a choice between a 7 and 5-membered ring. So both of them would be okay. For this one, which side is going to be our enolate? The left side or the right side? In terms of this whole chunk. The left side, why? Why is the right side not going to form an enolate? no alpha hydrogens. So we know that this bit is going to be the electrophile. And so if we do on the outside, we would get our 7-membered ring. And if we did it on the inside, we'd get our 5-membered ring. 5 is a little bit more stable than 7, but they're kind of a toss-up. So we wouldn't control the chaos a ton here. The last thing that we could do, which is tested a lot in other classes, we don't really do this, is what if you made a reaction mixture where you made your enolate? And we typically did this with LDA, that's the main one that's done, which is just a strong base. And you then just had a beaker with only enolate, and then drop-wise, you added in what you wanted to be the electrophile. So that way, even though this thing, if they were both in the same reaction beaker at the beginning, when you were forming your enolate, this could have formed enolates, right? It could have been a nucleophile. But when we're adding it drop-wise to something that already has the enolate formed, then we are only going to get a single product, which is nice. But again, y'all don't need to worry about this. I was just kind of wanting to present it as a way of controlling the chaos. We are on to our last topic of the last section, which is very sad. I should have saved the sentimental That's So Raven one for before. Maybe I'll end it on like a... So, we've covered the big ones, the aldol, the Claisen. We've talked about why these are kind of so complicated and dense. And so the last thing to talk about is just enolates can attack a lot of different things. There are a lot of kind of specialized reactions that they can do. And so I'm going to touch on a few of these here with y'all. So, if you have an enolate that attacks an enone, it will do 1,4 addition. And we call that 1,4 addition a Michael addition. Typically, the enolate nucleophile that we use is a dicarbonyl. And the dicarbonyl just helps it be more selective for the 1,4 position. It's kind of bulkier. So, you would form your enolate first, and then your enolate would do conjugate addition. So it would add at the end of the 1,4 system and push up. And then after some enolate steps, I think actually in lecture, Tim showed another step where like, hey, yes, we would solvate this, but then we would have another step where, we formed a dicarbonyl with an acidic hydrogen, we're gonna have to deprotonate that and then reprotonate that. So I did not show that, but this one also has a #annoying step. I'll do C lecture notes. So, the thing that you're going to look for in this, the characteristic product of the Michael addition, is a 1, 2, 3, 4, 5 between two carbonyls. So we would call it a 1,5 dicarbonyl. And the way that this is like characteristic of this reaction, it has to do with the spacing of a 1,4 like enone and the alpha carbon here to the other carbonyl. So that's where we get the 5. So it's going to be important to spot these functional groups that are these new kind of bigger picture ones. Another thing that we can do that we saw very early on in this section is we can just do a simple SN2 attack of we form an enolate, the enolate does a backside attack. And that we've done an alkylation. We've added some carbons here with a single bond. Now, we can also do something that looks like this if we like somehow reduced a enone. Like we could do an aldol condensation and reduce it. And that's like what we saw over here in this step where we reduced it and it looks like it's just an alkylation. Again, y'all are not really responsible for this reagent as a tool to use. So if you see something on especially an exam or a practice exam where you've just added carbon single bonds and it looks like you've added an alkyl group, you've only done an alkylation. We haven't tried to trick you with a reduction. Does that kind of make sense to the point I'm making? Okay. Then we have one of the my favorite reactions, decarboxylation. So this starts off with a keto ester, a beta keto ester, and you start off with an ester hydrolysis, so NaOH H2O, and then we start an H+, and that is going to turn your ester into a carboxylic acid. And that's our lecture 5, ester hydrolysis. And maybe I'll say with SN2, that's our lecture 6. And then our enolate chemistry, this is like lecture 3. Or sorry, not enolate chemistry, our enone chemistry, attacking 1,4 systems. So I really like how this lecture kind of intersects with all these other reactions that you've seen before, which makes nice, fun little like connections. So once we do our ester hydrolysis to a carboxylic acid, we do this interesting cyclic reaction here, where we have this kind of 6-membered ring transition state. And here you can imagine like there's like a little hydrogen bond that forms between these. And this is actually in like a chair structure, which makes it even weirder. Like you can imagine the O, H, and then, oh gosh, am I going to be able to draw it? Like this. So this is in a 6-membered ring transition state. It's like a chair structure. We won't ask you to draw the chair. I just think it's cool. But what happens is this carbonyl can go up and grab a hydrogen. The electrons in this OH bond fold down, make a carbon-oxygen double bond, and then we kick off this carbon-carbon bond onto our like enol position, or onto our carbonyl. And so you can trace like all the MO interactions. But at the end of the day, what you get is this, which is CO2, a gas. And we've already seen before, like in the chlorination in alcohol, when we can kick off a gas, it's super, super favorable. It drives the reaction forward. So like super favorable in terms of like delta G. And then we form an enol that then we could kind of tautomerize back into the ketone form. So really cool reaction. I really like the decarboxylation. And then the last one that I'm going to show is just more of a reaction scheme, kind of an idea for a set of reactions. And that's this monic reaction, which I think Tim called the manic reaction. But I think that this is, well, and a lot of people do. But I think that this is like a German name. And German, they don't have like that's not like a vowel that they have. It's monic. German. I sing in German, like I do like German diction, so I'm like, oh yeah, the double would make it a short vowel rather than a long vowel, but here we are. So, the things that we need for a monic reaction, or the kind of classic example of a monic, is a ketone, an amine, and an aldehyde. What first happens is an amine and an aldehyde come together, and using our lecture 5 reaction, form an aminium. Then, our ketone undergoes keto-enol tautomerization to make an enol, and we're doing an enol because we're in slightly acidic conditions. So we are not going to be doing an enolate. And then the kind of big step is the enol would push down and attack the aminium. And then after a few other kind of protonation, deprotonation steps, actually, no, I think directly, it would form this product. No, I lied to you. We would form this, and then we would deprotonate it. So the functional group that we have here at the end is at the beta position, because we've made a new alpha-beta bond. We have an amine on it, and so this would be a beta-aminocarbonyl. But this reaction scheme accomplishes a lot of things at once and combines a lot of reactions. So this is one that I always think is a really great final exam question, because it lets you do some lecture 10 chemistry, it lets you do some lecture 5 chemistry. And I think that there's a monic reaction on one of the practice exams. I don't know if I mentioned at the start, but the printed paper practice exams are on the back table. So as you're leaving, please get the printed copies and work on the printed ones rather than just using the iPad version. The PDFs are going to be available though. So this is challenge problem 6, just to give you some work on getting another challenge problem to get a head start. And do we see a beta-aminocarbonyl in our product? Do we see a carbonyl at all? No. So, how do we know it's a monic reaction? Well, what functional groups do we have present in our starting material? We have an amine. What else? Or an aldehyde here, yeah. And so why don't we start the monic and see kind of what would happen? Well, if we have like this aldehyde and an amine, we would say that would go to an aminium. And let's check it. So here, where is this green nitrogen in the product? Probably up here, right? Like it's probably not this one that's stayed in the ring. And then if we label the carbonyl carbon here, does this seem plausible if we like count around? So like a 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. That does seem to line up, right? So when you're doing the mechanism, you can do your amine formation all the way back from lecture 5, and you will have to actually draw out on the problem set, but just for the sake of time to get you started. Yep. This one. So we form that little ring. And in our monic reaction, this is where an enol would go and attack the aminium. But we don't have another carbonyl, we don't have an enol. Maybe let's look here and see where do we need to make a bond. We need to make a bond between the blue carbon and what? Yeah, this one right here. The other double bond. And what do we actually have right here? We have an enamine. And remember, enamines function just like enols. So we have a lone pair here that can push down and help this go and attack. And so that's going to be our kind of fundamental thing. We have an enamine instead of enol. And so that's going to be like the trickiest part about this mechanism. The rest of it, I think that y'all can finish up. We're not going to do this skill builder, but maybe I'll just comment on, oh, in our starting material, we have an ester. We have 2 carbonyls. How many carbonyls do we have in the product? 1. So what reaction do you think we've done if we've poofed away a carbonyl? Yeah, it's on the milk carton and we have just an ester gone missing. So this is doing some sort of decarboxylation. And then also, here we have some alkyl halide and we have this alkyl group added. So we're doing some sort of alkylation. Wait, I just said that, alkylation. The last note that I kind of want to end off on for section is a lot of these reactions look very similar, and one piece of the challenge is just going to be figuring out what happened. So which reaction took place. And so getting to know these new functional groups is going to be really important to help spot which reaction happened and to help kind of tag and target that to the mechanisms that you are learning. So again, we have our enone and our aldol from the aldol reaction, beta dicarbonyl for the claisen. The monic is the beta aminocarbonyl. Ketone here, missing a carbonyl, that's decarboxylation. Adding an alkyl group, alkylation. 1,5-dicarbonyl Michael. So, with that, that's the end of section. Oh my goodness. I want to leave off just with a couple quick comments. I've really enjoyed this summer. Like, I really, really enjoy, like, S17 in this class. I've enjoyed getting to know y'all. This was the class where I first realized that I, like, liked teaching. And, like, it is so rewarding to just get to work with y'all and to support y'all through this intense experience, which has been an intense experience. And so y'all are on the last week. I know that y'all are probably really tired after the exam. Please make sure to catch up on some rest this weekend, and then you'll get reset, re-energized going into the final. The exam 2 grades are going to come out Monday, but that's, I think, all I have for y'all. I'll still be around next week with office hours and such, but thank you for coming to section. Yeah. Yeah.